This is part 2 of lecture 7. In part 1, we learned about the different types of filters, the four major filter types: low pass, high pass, and band stop filters. We also learned about their characteristics, their features, frequency response plots, both for the ideal and the practical filters. And in this part, we learned about how to construct filter circuits that will realize the characteristics of the different filter types that we have learned in part 1. Now the filter circuits, depending on the components that are used to construct the filter circuits, it can be classified into two different types. One we call the passive filters, the other is the active filters. The passive filters are constructed using only the passive components. So if a filter circuit is constructed using only passive components, that is R, L, and C, then the filter circuit is called the passive filter. And if a filter circuit uses, along with the passive components, also the active components like the transistors or the op amps, the filter circuits that will use the active components along with the passive components are known as the active filters. So active filters have some advantages over the passive filters. They can also amplify, minimize the losses, as you will see in our lectures later. So first we will start with the passive filters to understand the fundamentals of the fundamental principles behind the design and construction of the filter circuits, how they realize the characteristics of the filters that we have learned in part 1, and then from there we'll move on to the active filters. Simple RC circuit can be used as a filter circuit. Depending on from where you are taking the output, it can work either as a low pass or a high pass filter. Now here in this diagram we are showing a simple RC circuit. The input Vi is applied to the terminal of the resistor R, and we are taking the output V0 from across this capacitor. Now the question is this circuit a high pass or a low pass filter? How it will work? So how do we know if the circuit is working as a high pass or a low pass? What is the mechanism to find that out, right? So that is not difficult. We can easily verify that if it is a low pass, if it is working as a low pass filter or as a high pass filter. So we need to examine the circuit just at two frequencies, one at very low frequency, that is zero frequency, the other at very high frequency, that is infinite frequency. So if we test the circuit at the output of the circuit at these two extreme frequencies, we can easily estimate the type of the filter, whether it is working as a low pass or a high pass filter. So let's say frequency is 0 at the beginning. So if frequency is 0, then the reactance of the circuit Xc, which is 1 over omega c, will be infinite, and infinite reactance means open circuit. So capacitor at 0 frequency will behave like an open circuit, and this is well known to us that the capacitor is open for DC, that means 0 frequency. So capacitor will behave like open circuit here. This shown in the diagram, capacitor is open, and as long as the capacitor is open, there will be no current flowing, and as long as there is no current flow in the circuit, there will be no voltage drop across the resistor R. So V0, whatever the output voltage here, will be same as the VI's. Since there is no voltage drop across the resistor R, so the voltage at the output terminal will be same as the voltage at the input terminal. So V0 is Vi. So what we have got, that at zero frequency with the output is same as the input, and the transmission in this case V0 by Vi will be 1. That means we get 100% transmission at zero frequency. Now we need to also examine what happens at high frequency. In this case, we will test at the infinite frequency, that is the extreme high. So if frequency is infinite, then reactance is 1 over omega c becomes 0, and 0 reactance means short circuit. So capacitor will behave like a short circuit at very high or infinite frequency. So when we have the output terminal shorted to ground, so that means V0 will be 0. There will be a flow of current, but there will be no voltage at the output terminal, because the output terminal is shorted to ground. So what we have got here, that at a very high extreme frequency, capacitor becomes short circuit and output voltage becomes 0, and the transmission V0 by Vi will be 0. So at zero frequency we get 100% transmission. At extreme high or infinite frequency we get 0 transmission. So from this we can have an estimate of the feature of, or the characteristics of this filter circuit, and we can draw it like this, that at zero frequency we have 100% transmission, magnitude is 1, and as you increase the frequency, the transmission will start decreasing and decreasing, and it will approach 0 at very high frequency, and it will become 0 at infinite frequency. So this is how it will look like, what is also known as the frequency response plot for the low pass filter. So this is the circuit here will work like a low pass filter, and that's what we call passive RC low pass filter. Okay, so next we'll see. So now we would like to see what happens if you exchange the position of the resistor and the capacitor. Now we are applying the input at the capacitor terminal, and we take the output from across the resistor. Now how the circuit will behave now? Will it behave like a low pass or a high pass filter? How do we find out? So that is not difficult to find out. Again, we can test the circuit at two extreme frequencies, and we can easily find that out. So we start with the zero frequency first. At zero frequency, the reactance of the capacitor will be infinity. So when the reactance is infinite, the capacitor will behave like an open circuit, and that is how the circuit will look like. And you can see the output terminal has no connection with the input, totally disconnected, and output is grounded. Through the resistor R there is no current flow, and so the voltage here will be 0. So at zero frequency, now we get 0 output, and so the transmission will be 0. So no transmission at zero frequency or low frequency. Now we check at the other extreme, at very high frequency or infinite frequency. What happens? Frequency is infinity, so reactance of the capacitor is 0, and that is how the circuit will look like. Now the capacitor will behave like short circuit, and output terminal is now shorted to the input through the capacitor. So whatever voltage you have at the input, you get same voltage at the output. That means V0 is Vi, and so the transmission magnitude now is 1. So you get high transmission at high frequency. and zero transmission at low frequency. So the circuit will behave like a high pass filter. So this is we call passive RC high pass filter, and we can estimate about the frequency response plot of the circuit from our this analysis. At zero frequency we have zero transmission. At very high infinite frequency you have 100% or transmission magnitude will be 1. So as you increase the frequency from 0, the transmission will start rising, it will keep rising, and it will approach 1 or 100% transmission at very high or infinite frequency. So that is how the frequency response plot will look like for this high pass filter. So now that we have learned how to construct the low pass and the very basic low pass and high pass filter circuits using the R and C circuit, our next step is to derive the expression for the transfer function of these circuits that we will use again to extract the cutoff frequency or the important features of the filter circuit. So here we have the high pass filter circuit that we have just examined, that it and this RC circuit works as a high pass filter, and with the frequency response plot looking like this. So what is the transfer function for this filter circuit? First, to find the transfer function, we start with the expression for the output voltage. The output voltage we can express like this, applying the voltage division rule. This is just a simple series combination of R and C. So applying the voltage division rule, we can express V naught as a function of VI like this. After simplification, you divide the numerator and the denominator by R. So this we can express like this. And from this, rearranging the terms, we can get the expression for the transfer function. V naught by Vi is this. So this is the expression for the transfer function, which is a function of frequency, which is j omega. So we write T as a function of j omega is this. So this is our expression for the transfer function. And from this we can verify if it does satisfy the requirements for the high pass filter, that is zero transmission at very low or zero frequency, and high transmission, the 100% transmission at very high or infinite frequency. So for that, what we need to do, we need to determine the magnitude of the transfer function. We take the modulus of this transfer function, and then we get this, and that when you take the modulus of this one, so this reduces to this, and I mean this is just a plus jb is a square plus square root of a square plus b square. So you are supposed to know this, the modulus. So that is how we can express the modulus of this, and from this expression you can evaluate the magnitude of the transfer function for any frequency omega. So this is a complex quantity, so we have taken the absolute magnitude, and now we can evaluate this for any frequency omega, and we can determine the magnitude of transmission. So we just check at two extreme frequencies, and we'll show that it does satisfy, right, this plot what we have for our high pass filter. So if the frequency is 0, if you put 0 here, then this term becomes infinity. 1 over 0 is infinite. So you get infinity here, and 1 over infinity will be 0. So at 0 frequency, this expression will become 0. So transmission is 0. So what we have here at 0, it should be 0. So that's what we get from this expression. And if frequency is infinity, when frequency approaches infinity or very high, so this 1 over, here you have infinity and this becomes 0. So this part becomes 0, so you have 1. So 1 over 1, it becomes 1. So at very high or infinite frequency, this expression, the magnitude of this expression will be 1, or it will approach 1 at very high frequency. So what we get here, that this expression, magnitude expression of the transfer function, it does represent this variation of this frequency response plot, that at 0 frequency you will have magnitude 0, and at very high frequency it will approach 1. So next we'll the transfer function for the low pass filter, and so this is our passive RC low pass filter circuit, and with the frequency response plot like this, at 0 frequency you have 100% transmission, and it gradually decreases and approaches 0 at very high or infinite frequency. Again, to find the transfer function, we start from the expression for the output voltage, applying the voltage division rule. We express V0 as a function of Vi, and from that, rearranging the terms, we can express the transfer function V0 by Vi like this. So this is our expression for the transfer function for this low pass filter, and from this also we can verify if it satisfies the requirement for this low pass filter, that is, should have 1 or high transmission at low frequency, and it should have very low or 0 transmission at very high or infinite frequency. So for that, again, we need to take modulus to find the absolute magnitude of this transfer function, and that we can express like this: when you take modulus a square plus b square, and then evaluate this at different frequencies to find the magnitude. We evaluate at two extreme frequencies. One is at 0 frequency and the other at extreme high or infinite frequency. So what happens at 0 frequency? If you put 0 here, so it becomes 0 and the magnitude becomes 1. So at 0 frequency you get transmission magnitude 1 or 100% transmission. The other extreme, when frequency is infinity, if you put infinite here, it becomes 1 over infinity and you get 0. So at infinite frequency the transmission magnitude will become 0. So it does satisfy the requirements of this frequency response plot. At 0 frequency you have 100% transmission, and with the increase in frequency it will gradually decrease and become 0 at very high frequency.